Okay, model of biomedical instrumentation or devices. Okay, for biomedical instrument, normally they are mixed between mechanical, electrical system, and also some, of course, some biological process. Okay, so we try to investigate how some of the medical equipment or medical device work. Okay, for example, example one, we're going to discuss about dialysis weight measuring circuit. So not the whole process of dialysis, that's beyond our scope. So because we want to model the electronic part or mechanical part of the uh, electronic device. So let's say we have this circuit, we have this diagram. So this is the raw, the let's say supply. Okay, we're going to supply to human body here. Okay, so before we supply, we should um, increase the temperature so that the temperature will be, the output here will be equal to the temperature of human body. Okay, so that the body can accept easily. Okay, so we have, of course, the valve control here, so that it doesn't flow backward. Okay, so we have the pump, so that the pump we can control uh, together with this valve, so that it can control the speed that is go through the human body. Okay, so when the temperature is regulate into the normal human temperature, human body temperature. So we pass through the dialysate to the human body, okay, and then after use inside the body, then it will pass it back. Of course, different routes, okay, and the waste will be pumped out by this pump to the span dialysate tank here. So our task here is to measure, how to measure this, to make sure that the body have received enough dialysis treatment. Okay, so so we just only want to model this part. Okay, this part only, the electrical part of that. So inside that we have a circuit like this. So we have the supply of 15 volt, and this is a resistor. Okay, just a thermostat here. Okay, and we're going to wait the dialysate, the waste dialysate. Okay, we put a load here. So initially it start somewhere in the middle here. Okay, so when we add more and more dialysate, then this spring will go down, and similarly to the real start here, it will go down until it reaches zero. Then that means it's complete the process. Then we're going to stop the supply. Okay, so that's the process how we measure that. So the circuit, this is the circuit that control the operation here. So it will be automatically control when there's enough, when the body have enough treatment. So we supply everything, so it will control here. So the span dialysis here, we control here. If the amount is enough, so we're going to stop automatically. So the control element will be here. We measure what is the waste out there. So this is the circuit to control that. Okay, just a very simple circuit. Okay, at the beginning, this arrow will be in the middle here. So as the weight increase, then the spring will be go down, down, down until it reach at this end. So there's no more input that will be supplied to here. Then we connect this to switch to off the switch. Okay, and we can control the gain of this using this RF divided by RI. So we learned that already previously for op-amp. So this is because the input is connected to plus terminal and the minus terminal is grounded in this case. So this is non-inverting amplifier. So the transfer function, as we discussed previously, supposed to be 1 plus RF divided by RI. So this is the transfer function for this. Okay, so this is one of the electrical devices, and this is the control element that we use. So the control elements is quite simple. So we use this to control, to make the process automatic. So after it's enough amount of dialysis, then it will turn off automatically. So we don't have to monitor that. Okay, second example is an integrator for EMG signal. So EMG signal is the muscle signal. So let's say we want to do exercise to burn energy or for regular exercise or anything. If we want to measure, so the tool is called integrator for EMG signal. So how are we going to measure whether we have spent enough time or work, produce enough work so that we spend all the required energy that we should perform. Okay, so this is the circuit, how we're going to count that EMG signal. So we measure the signal, EMG signal, okay, and then we put into absolute circuit. So absolute circuit is nothing, just to invert the negative into positive so that everything become positive so that we can integrate later on. Okay, and the one that we concern here is within this square dotted line. Okay, this is then what we call the integrated circuit. Okay, so how the circuit work is like this. So we're going to supply this to the negative terminal, okay, and positive terminal we ground. That means this is inverting op-amp, so we expect the output to be negative, okay, compared to V2. V2 is positive, so V3 going to be negative. So we start with 0 for V3 here, and then it's going down. Okay, so how the counting happen? Okay, as we supply this, that means if we do the exercise, then we're going to supply the current here to charge this capacitor. Okay, to charge this capacitor. When this capacitor become more and more charged, that means the gain or the transfer function for this op-amp, if you still remember, is here V3 divided by V2 is equal to Z2 here divided by Z1 here. So as we charge C further, then this 1 over C become smaller. Okay, become smaller and smaller. So C, the gain become smaller and smaller. So originally V3 and V2 will be exactly the same. So okay, so the gain here, the V3 here is equal to 0. So as we charging this, the top part will be large. Sorry, the C will be large as we charge, and then 1 over C become smaller. So V3 becomes smaller and smaller because the gain also become smaller and smaller in terms of magnitude. Okay, so as this value, as this impedance goes up, okay, so V3 become smaller and smaller. So we have the comparator, another op-amp here. We set the value here. If the value is the same as this one, our setting value, then it will send a signal to this monostable vibrator. Then this vibrator will turn on the switch and also give the signal to this counter to count once. So if the V3 equal to V2, that means we're going to reduce this V3 again and again until the value of V3 equal to Vt. So when the value is the same, then it will give one signal. Okay, and then the switch will be on here. When the switch is on, then this C will discharge because we short circuit. Then we reset this to 0 again. Okay, and then we start to accumulate again until it will produce V3 equal to Vt here, and the comparator will signal again. Then the switch will be closed, counter will be up, another one. Okay, so the process will go through. That's how we calculate the amount of work that has been done by EMG measurement. Okay, even though we can see here the signal of EMG doesn't produce the exact or constant volume or constant amplitude. Okay, it doesn't matter because we accumulate the charge here, not the voltage, but we accumulate the charge. So if the exercise is small, then it will take longer time for us to operate this switch, okay, automatically. So if the exercise is extensive, that means this peak is very large, then it will take shorter time. So by that, we're going to count the amount of work that has been done by the person, not how long it work or exercise, but we measure the actual work or energy that has been spent for that exercise. So this is what we call EMG integrated signal. Okay, it's quite intelligent. So if you work or exercise very hard, then you can easily get the number of count here. But if you work very slow and the movement is very small, so it will take longer time. Okay, so this controller circuit is again transfer function is very easy. So this is what is the controller circuit. Just a normal op-amp transfer function, inverting op-amp transfer function. So that's why you have minus there. So just take this Z2 divided by Z1. You have this transfer function. Okay. Another example is an ECG amplifier circuit. So if you measure the ECG, okay, ECG for the heart rate or heart signal. Okay, for the heart signal here, so you connect the lead. This is the minimum, the 5 lead you connect to a body, a human body, and then you connect this to a resistor and switch, or we call this part as, including the op-amp, is conditioner circuit. So you should connect a right resistor with a special ratio, and also filter the noise filter here, special circuit, we call it conditioner circuit. So if you want to know detail about this, you go and Google conditioner circuit for ECG amplifier. So after we do conditioner, connect to conditioner circuit here, so output become clean and manageable. So over here is very raw, so it's very difficult for us to see the signal. Okay, so after the conditioner circuit, then the signal is clean. Okay, so we put into amplifier, so that it will be up to the normal operation of processor, which is normally within 0 to 5 volt. Okay, the output here is very small, maybe millivolt. So we need the open to amplify that. But we don't want to amplify everything, including noise. That's why you have this circuit, conditioner circuit here, so that we're going to clean the signal first and remove all the outliers and also bias, okay, into the signal. So you get a clean signal here, the real signal, but still very small, normally millivolt. So we're going to amplify into a normal range of the signal that we can display, which is normally between 0 to 5 volt. Okay, and then we're going to use ADC. So the signal here is still analog, so we're going to convert that into digital. So analog to digital converter here, and then we put into microprocessor or signal processor, can be nowadays maybe single board computer. Okay, so it can be any DSP board. Okay, processing. Anyway, this board will do the processing of this. So what you want? You want to store the information, or you want to display the information in monitor, or you want to print the signal. Okay. So as usual, over here you have amplifier circuit, so you can model this. Unfortunately, this one is the signal conditioning mostly is a filter. So we have another example of filter later on. Okay, so for the amplifier circuit, so normally we have a basic, at least something like this inside the amplifier part. So every signal that come in, so VA, VB, just now we have 5 signals. So we have 5 signal come in like this, so we should have another 3, okay, of this, something like this at the bottom. So inside that we have a signal and amplifier also at the end here. Okay, so this is just a common amplifier. Okay, if you see here, for example, for the first op-amp, this one, so the input is applied to plus, so we know that this is non-inverting amplifier. So when non-inverting amplifier, so the transfer function is supposed to be 1 plus something of this ratio. Okay, ratio of Z2 divided by Z1. So in this case, Z2 is here. Okay, Z2 is always the part of the circuit that part of the component that we connect to the output. So the output for this here is R2. Okay, so R2 must be equal to Z2. Okay, and then the circuit that we finally connected to the ground, okay, is always Z1. So now ground is here, so Z1 must be this one. Okay, but now we have two R1 because one is belong to this one and one belong to this. Okay, so this is the transfer function for this one. Okay, this one also similar because all the arrangement is the same, so transfer function for this also same as this one. Okay, about this one. Okay, this one, look at the input. So the input is connected to positive, and you have also input connected to negative there. Okay, but look at this. Okay, you have the transfer, you have the component there, and the input is connected to here. So that means the transfer function for this is going to be inverting because we control using that. So it's going to be inverting amplifier for that. So G3 equal to this one. Okay. So the first two is non-inverting amplifier, and the last one is inverting amplifier. So when you multiply, you're going to get something like this. But of course, these two is in parallel, and you put into that. Okay, so you have two in parallel, G1 and G2 from op-amp 1, op-amp 2. Okay, multiply with the third multiplier, which is inverting. So you get something like that. Okay, so it's nothing new. It's just a normal op-amp transfer function. Okay, just to know the structure of that, and of course you can model. So that it's indicate that inside the biomedical device, you're going to see some electrical component like this. But of course, if you want to know about the mechanical part, but in this case, there's no mechanical part. But for example, in this case, also no mechanical part because you measure straight away, then you can get electrical signal, okay, straight away. But if you have mechanical part, then you have to do the mechanical modeling also.